yourself a link if you want that link to La Brea Tar Pits. If you ever go down south, if you have a reason to go down there, it's actually worth just going down for that, honestly. But if you don't want to, I understand. So today, what are we doing? We're talking about limiting and excess reactants and something else called percent efficiency or percent yield. And then we'll do some more on the brownie packet. We're going to do some more of that tomorrow. I'm going to record some stuff on that and have you do some of the calculations on the packet. The whole packet will not need to be completed, but more of it tomorrow. So, and then Thursday, it'll be due when you walk in the door, and I'll go over the answers with you. All right. So if you are at home, this is in your feed. If you are in the room, this is for you. I think that's the Uh-oh, that quarter had a bad time. What happened? You bent it? What? You animal. Seriously? Seriously?
Well, ask Colin.
No, he put it in the concrete.
What the heck? I can't even open a jar of pickles. Never mind, bend a quarter. Good Lord of mercy. All right. So limiting and excess reactants. So really, I think it's a pretty easy concept, but let's just see if you think so too. Goodness gravy. All right, crazy example. So we're backing off of the food examples here. Start this section off with a cabinet maker, a carpenter that is trying to make tables, 4-legged tables. And he's got 2 tabletops, and he's got 7 legs. And the question is, how many tables with 4 legs can he make? So our recipe is 1 tabletop plus 4 legs makes 1 table, for example. Totally silly, right? So how many tables can he make with these ingredients? Just 1, right? He's going to have a leftover tabletop, and he's going to have 3 leftover legs, but he can only make 1 table because this is what the recipe requires. Okay. Same kind of thing happens in chemistry. And when you're cooking, when you go to cook and you open up your pantry or your fridge, sometimes you have extras of all the ingredients, actually. Sometimes you only have, barely enough of one or not enough of one. And you have to scale everything back. So same kind of thing happens when we're doing chemical reactions. So in a chemical reaction, there's probably going to be something you don't have a lot of, an insufficient amount of it. And that's called the limiting reagent. So reagents, I guess a new word for you guys, it means the same thing as reactant, basically. It's just something that reacts together with other stuff. So reagent, we're going to use it synonymously with reactant. Okay, and those added together make our products, of course. The limiting reagent is the one that limits how much you can make. So in the case of the table analogy, it's the legs that limited us. We had enough tabletops. We didn't have enough legs to make 2 tables, right? So that's their little thing. Okay. Sometimes you will also have lots of extra, right? If you go to the store, if you like to do baking, you know that you don't buy flour a cup at a time. You don't buy 1 egg at a time, right? So you buy 5 pounds of flour, 5 pounds of sugar, maybe 10 pounds, I don't know, a dozen eggs. You usually or can often have more than you need. That's excess, okay? So excess reagent or excess reactant is stuff you'll have leftovers of. it is possible to have leftovers of all of your reagents, but one of them is going to limit how much product you can make. Typically, it's the one that's most expensive. So not every manufacturing plant is going to want to have the really expensive stuff just in storage. So they'll buy lots of extra of the cheap stuff, and then the expensive stuff, they only buy what they need. So that's one other thing to keep in mind too. Excess is a multiple letter word. You can just abbreviate it with XS. Okay, so that's just a cutesy little abbreviation to speed up your note taking if you would like to use it. All right, let's go back to brownies though, because those are more fun. So if your recipe says you need 2 sticks of butter or margarine and 4 eggs, you go to your refrigerator and you have 1 stick and a dozen eggs. Obviously, something's going to limit how much brownies you can make, right? Which one? The butter. The recipe says 2 sticks. You've only got 1. Can you still make brownies? Yeah, just half as much, right? And so you'll have lots of leftover eggs. You'll actually have 10 leftover eggs because the recipe calls for 4, but you're only doing a half, right? So you'll have a lot of leftovers. Everybody get that? Okay with that? Okay. All right, let's go to our favorite reaction, the reaction to make ammonia. The reaction requires 1 nitrogen molecule, 3 hydrogen molecules to make 2 ammonia molecules. Now, you don't go and get 1 molecule at a time, but just pretend, right? Okay. So if you go to your cupboard and you've got 2 nitrogens, 3 hydrogens, how much ammonia can you make? Only as much as the hydrogen lets you, right? You're going to have leftover nitrogens, because 1 nitrogen molecule is needed and you have 2. You're not going to have any hydrogen left over because you need 3 for the recipe and you only have 3. And you can only make 2 ammonias, even though you have enough nitrogen to make 4. You don't have enough hydrogen. Okay, so limiting reagent, which one is it? What's limiting our product? Hydrogen, right? And the excess is the nitrogen. Yes, sir.
This is usually 3 molecules of H2 or H3.
H2?
So how did you get it to H3 with this?
It's just like you have to buy them 2 at a time, okay? But you can use them 1 at a time, 2 at a time, 3 at a time, 4 at a time, 5 at a time. It depends on the stuff you're trying to make. Okay, it doesn't matter how they come from the hydrogen store. Okay, you can use them whatever it takes.
So if you get 2 things of H3, 3 things of H2.
3 things of H2.
Okay.
And then they have to come apart, and then they stick to the nitrogen. So remember, nitrogen has 5 valence electrons, but one of those is a lone pair. So this is my ammonia molecule, right? And then hydrogens stick to those other electrons. So, yep. All right, percent yield. When you talk about batting averages, that is a percent yield as well. It's the part out of the total possible. In terms of a chemistry reaction, the percent yield is how much product is made based on how much you should make. And I could tell you for sure, without a doubt, there are no 100% efficient reactions, period. You will never get 100% of what you're supposed to get. Okay, it's just how it is. And probably some of you have experienced that if you've ever done any baking. Probably not as bad as me, but make some chocolate chip cookies. Really hungry brownies and cookies. You get some chocolate chip cookies and the recipe says you make 5 dozen. I don't know about you, but I never make 5 dozen cookies out of my cookie recipe. How come? Big cookies, but mostly because I eat the cookie dough. So some of it falls on the floor, some of it sticks to the bowl. a lot of it goes, don't eat cookie dough. Raw cookie dough is bad for you. It can kill you. Salmonella. I've done my good deed, but I'm still here. So I will tell you that it doesn't necessarily kill you, but it could. So I have to tell you that.
At this point, a lot of things can kill you.
That's the truth. Life, you don't get out of it alive, right? So be careful for salmonella. Chicken, eggs, you know, whatever. Oh, well. Anyway, I never get the full amount of cookies because I eat the cookie dough, okay? But again, you're going to spill something. You're going to have stuff left on the containers. All the molecules in a real reaction aren't going to find each other. Okay, so honestly, 60 to 70% efficiency, percent yield is a really excellent percent yield for chemical reactions. Also, even though we always draw reactions going one way, in reality, every reaction can also go backwards a little bit. It's kind of weird. Okay, so what's the percent yield? If you get 43 cookies and you're supposed to get 60, what's your percent yield? Calculate it. Go. How much do you think you're going to get? What's that?
71.
It is 71. How'd you do that?
I just divided 43.
Perfect. 43 by 60 and times it by 100 and 71.67%. Everybody agree?
Yes.
Hopefully. That's the percent yield. Not perfect. Over the nose, please. So theoretical yield is what the recipe, the balanced equation, tells you you're supposed to get. The actual yield, unsurprisingly, is what you actually get. Okay. And you have the equation on your paper, but I'll write it one more time. Percent yield is the actual yield divided by the theoretical from the balanced equation and your stoichiometric calculations. And of course, for percent, you multiply by 100. Part over the total times 100. And again, if you're getting 60, 70%, that's a really good, efficient reaction. So that means if you're manufacturing something, paint or some whatever chemical that you're making, you're going to have a lot more reactants than you think you need for your products. So they have to factor this in when they make stuff. Okay. So again, percent yield, I have it up here. You have it on your papers. It's just the ratio of what you really get compared to what you should get. Times 100. Okay. So there's a fun little activity that we don't have time this year to do using Alka-Seltzer tablets. And last period was the first period anybody had ever heard of Alka-Seltzer tablets. Do you guys know what Alka-Seltzer tablets? Some of you do. Oh, cool. What's that? You can clean your retainer with it. That is true. And effervescent tablets work because, oops, this one's broken. Because they have an acid and a base. And one of the things that they have in them, and unfortunately these are all broken, one of the things that they have in them is baking soda. And you guys know that if you put baking soda and an acid together, you get bubbles, right? Sodium hydrogen carbonate is the chemical equation or chemical formula for baking soda. H3, this is a crazy one, C3H5O7. This hydrogen's at the front, meaning it's a acid. Okay, so hydrogens for the cation ions means it's an acid. You don't have to know what this is to know its charge. Got 3 hydrogens stuck to one thing. What's the charge on this one thing? -3. C3H5O7. Remember, we want to get to 0. Okay, that's the citrate ion. You have no way of knowing that, but you know, you also should know by now that, you know, these guys are positive for sure. And then one of these, there's only one because there's no parentheses, even though there's 15 atoms in this one ion, has the charge of -3. Well, they're going to do little innies and outies. It's kind of a weird one. So sodium comes off of here. Hydrogen's there. CO3 becomes CO2. And there's a leftover oxygen. But the oxygen doesn't go here. It goes here. And that makes hydroxide. Okay, so we get CO2 bubbles. And some other stuff. So Alka-Seltzer, I'm going to play this for you, is quite entertaining. And back in the day, there were some pretty funny commercials about Alka-Seltzer. So let me play you a couple real quick. If I can find them. Where did my, there we are. Not that one.
Something better for myself. I was starting to get comments from
Skip.
Plop, fizz, fizz, oh, what a relief it is.
Plop, plop, fizz, fizz, oh, what a relief it is.
And now a page from our Sunday morning almanac. February 21st, 1931, 79 years ago today. The day the market for over-the-counter medications literally bubbled over. But that was the day Miles Laboratories introduced a new antacid product called Alka-Seltzer. A mix of aspirin, bicarbonate of soda, and citric acid that burst into bubbles when plopped into water. Alka-Seltzer was an immediate hit, becoming both a popular remedy and a pop culture icon.
For relief from upset stomach, Alka-Seltzer.
Beginning in 1951, Alka-Seltzer's TV spokespuppet, Speedy, sang and danced his way through countless commercials.
Mamma mia, that's some species cut.
To be followed in the 1970s by human actors in a number of ads, including one that may just be the most famous TV commercial of all.
I can't believe I ate that whole thing.
You ate it, Ralph.
I can't believe I ate that whole thing.
No, Ralph, I ate it.
I can't believe I ate that whole thing.
Take 2 Alka-Seltzer.
So memorable was the campaign that Alka-Seltzer reprised it in 2005 with a subtle nod to the original.
I can't believe I ate that whole thing.
Oh, whoever heard that before?
These days, Alka-Seltzer is made by Bayer, and it has mutated from the original tablets into a whole array of products.
Plop, plop, fizz, fizz.
Still, the basic idea survives. Over package, plop in tablets, watch the fizz.
Oh, what a relief it is. What a relief.
Just make you just happy. Have you guys ever heard those commercials before? Oh my gosh, this one's hilarious. So back in the day, there was a whole string of them. I didn't realize this one was this old, but that it began on this thing. So I'll just play this for you because it's fun.
Mamma mia, that's some species cut.
Spicy meatballs, Jack. Sorry.
Take 28. Mamma mia, that's a spicy meatball.
Cut. The accent.
Huh. Cut.
Cut.
Missy, micey, bossy, falsy.
Take 59. And action.
Sometimes you eat more than you should, and when it's spicy besides, Mamma mia, do you need Alka-Seltzer? Alka-Seltzer can help unstuff you, relieve the acid indigestion, and help make you your old self again.
Mamma mia, that's a spicy meatball.
Cut. Okay. Let's break for lunch.
Anyway, Commercials used to be funny. Okay, anyhow. So there's a little history. You can ask your parents or grandparents if they remember the Alka-Seltzer commercials. Bet they'll say plop, plop, fizz, fizz. That's what I bet. What does that have to do with anything? Well, what that has to do with is this. So 2 dry ingredients. Don't do anything in the package. You put them into water and fizz, fizz. So that fizz, fizz, we could measure how much carbon dioxide is leaving, right? Carbon dioxide is a gas. It should be exiting the beaker. Some water is also exiting. Usually we put a cover on it. But the whole time that the CO2 is reacting, it's also leaving the container. The matter's still there. You just can't capture it. So there's a whole reaction that we do, that we've done before to practice limiting and excess reactants. There's a certain amount of CO2 that should form based on how much baking soda is in here. So let's see if we can balance this equation. All right, you have the equation written on your paper. I'll finish writing it. So the other thing that forms, and I'm going to do water this way, HOH. Okay, and then the sodium ions, which are +1, go with the citrate ions. So that means we need 3 sodiums. Oops. Yeah, 507. So there's 3 sodiums that go together here. So this is not balanced. Okay. Again, the baking soda breaks into sodium ions, hydroxide ions, and CO2 gas. And then this is our citric acid. So that's the acid that's in citrus fruit. You can also buy citric acid crystals if you want to, like if you do any canning of vegetables and stuff to keep your peaches from browning when you can them, that sort of thing. All right. Take a minute, talk to your neighbor, see if you can figure out how to get this thing balanced. So don't break up the citrate. Don't break that up. It stays as a unit. Okay? This stays as a unit. So let's look at this real quick. Michael, how many sodiums on the left? Uh-huh.
There's only 1.
And how many on the right?
30.
So what do we got to do? The coefficient, nicely said. So we know we got to have 3 baking sodas. Everybody agree? So that's going to give us Na plus another OH and another CO2. Okay, so we got our sodium taken care of. Check. We got 3 hydroxides now, 3 CO2s. Go.
I'm just confused. So it goes from CO3 to CO2.
That's what the bubbles are. So when you have bubbly water, that's seltzer water. Okay, so it's carbonated water. So carbon dioxide gas percolated through water makes bubble water. Throw in some sugar and some food coloring and you got soda pop. Okay. So this also happened, right? This is what happened. You put baking soda and vinegar and you make your volcano. Why does it make a volcano? Because the CO2 bubbles. You put calcium carbonate with acid and the CO2 comes off. Okay. Like we did with the, we did baking soda and hydrochloric acid in our lab. We did calcium carbonate, the little rocks, and acid too. Okay, so right now I know I've got 3 CO2s. So I should put a 3 here. Yes?
Yes.
Okay. And hydrogen goes with hydroxide, hydrogen goes with hydroxide, hydrogen goes with hydroxide. What's HOH? Water. So we got 3 of those. And now we should be good because the 3 sodiums are with the acetate here. So 3 of these baking sodas go with 1 citric acid, makes 3 CO2s, 3 waters, and 1 sodium citrate. Looks really complicated, huh? It's not too bad if you keep in mind how things break apart. Again, time you get a metal in front, it's going to be your cation. Okay, hydrogens. Everything after it, if it's not in parentheses, is 1 single unit. The little tricky part is here, but we've seen that twice before in the reactions that you did in the lab. So based on this, for every mole of citric acid, I should make 3 moles of carbon dioxide. And so we could calculate how many moles of citric acid this is and triple it, and then figure out how much CO2 we should have. So that is the gist of what we would have done if we had the lab. Questions on that? Okay, that's it for chapter 12 right now. So if we would pull out your brownie packet real quick. How far did we get? Did we get through the first page? Okay, awesome. So we got all of our recipe stuff done, right? All the eggs and flour and all that stuff. Any questions on the front page? Lovely. All right, so we're going to use the reaction we've been talking about a bunch. I'm going to write it on the board because it's faster. But we're doing the ammonia reaction one more time. So again, 1 nitrogen, 3 hydrogens makes 2 ammonias. Those are our proportions. The ratios, 1 of these goes with 3 of these to make 2 of these, right? The only place where 1 plus 3 makes 2. That's the same as moles. 1 mole of nitrogen goes with 3 moles of hydrogen to make 2 moles of ammonia. Excuse me. However, what if I told you you have 7 moles of nitrogen? Most of you probably pretty quickly will be able to tell me how many moles of hydrogen I need, but if you can't see it, it's totally fine. So this is your given information from the problem, and you're asked to find hydrogen. You need a conversion factor that has the asked for substance on the top and the given substance on the bottom. And so that mole ratio comes from our balance equation coefficients. What are you given? You're given nitrogen. What do you ask for? You're asked for hydrogen. The recipe says 3 hydrogens for 1 nitrogen. I need 3 times as many hydrogen molecules as I have nitrogen molecules. And of course, 7 times 3 is 21. So if I had 7 moles of nitrogen, and I wanted to use it all up, the recipe says I need to have 21 moles of hydrogen to do that. That's number 2. Questions? Okay. Let's try this one then. And question number 3, it's not asking about hydrogen, it's asking about ammonia. Here's how much nitrogen you have. How much ammonia can you make? So again, you're going to put the asked for substance on top, the given substance on the bottom. That mole ratio is 2 to 1. Every 1 nitrogen makes 2 ammonia. So if you have 7, you're going to make 14. If you had 100% efficiency, which you never do. Okay, so we're just picking out these numbers and using them as necessary. Okay, let's try one more. What if I had 21 moles of hydrogen? How much ammonia could I make? Ammonia to hydrogen from the balanced equation. 2 to 3. And magically, you guys should be able to see that, yes, you'd make 14 moles of ammonia. Okay, so we can look at it from any angle, okay, any part of it. Now, moles are great, but we need to be able to weigh things out or get their volumes. So the first thing we're going to do next is go ahead and find molar mass. So to find a molar mass of a substance, you have to use the periodic table. So we got nitrogen. I'm going to type it in right now so it lines up. Plus 3 hydrogens make 2 ammonias. Okay, so it's a 1 to 3 to 2 proportion. Oh, heck. How do you find the molar mass of nitrogen gas? You look on the periodic table, you look at the subscript, you say 2 times 14.01 equals 28.02 grams per mole. Same kind of process for hydrogen. Again, we're just for 1 mole of the gas, not balanced equation yet. 2 hydrogens, each hydrogen is 1.01. That means hydrogen gas is 2.02 grams per mole. And then for ammonia, you've got 1 times 14.01 plus 3 times 1.01, which of course is 17.04 grams per mole. Get rid of that. No, it won't fit. Strand. That fit last period. Oh, well. Okay. Everybody good so far? So if you look, that's 28 and 2, that's 30 grams. That doesn't equal 17. Did I lie to you? Nope, not this time. 28.02 grams. 1 times 28 is 28.02, right? 1 times 28.02. Okay, that's a coefficient 1. And then we got to do 3 times 2.02. That's 28 and 6, that's 34. And magically, if we do 2 times 17.04, we're going to get 34.08 grams. Now we're balanced. This ingredient plus this ingredient in the right proportions has the same mass as our products. Yes.
Okay, so you have the nitrogen, and you said there's 2, which it's diatomic, so it makes sense. But then there's hydrogen, which is also diatomic.
Uh-huh.
There's 3 of them. So how does that?
There's 3 diatomic hydrogens. Each one of them is 1.01. So this is 2.02, this is 2.02, this is 2.02. Yeah. Okay, we will go through how to do the other things tomorrow on the video I will share, and I will have you do one of the next pages. See how you do with those. Any questions from the home front?